Hello, everyone. This is Tom Ballard, the groundwater guy, here with Charlie Carner from Well Jet. Well Jet provides water well rehabilitation and well development services using a proprietary patented jetting technique, and I'll let Charlie dive in and give you all the details. But I can tell you that we have worked with WellJet in the past, and they are the consummate pros and do a great job. So, Charlie, if you want to dive in and explain, what your company does, a little bit about the technology, and I know you got a presentation, so let me just let you take it away.
Well, thanks, Tom. I appreciate that very much, and appreciate the opportunity to talk to you and to your audience about WellJet, about what we do and how we came to be, and how we function in the wonderful world of water well development and rehabilitation. This technology, as you mentioned, it is a patented high-pressure hydrojetting technique. It was invented by the president of the company that I work for, Hydropressure Cleaning. And as you can tell from the name of the company, Hydropressure Cleaning, that's what Jeff Glass has always done, finding ways to use high pressure and ultra high pressure water jetting to solve industrial problems. He's done it in the oil business on refinery shutdowns, hydro demolition in repairing bridge decks, surface preparation of aircraft carriers, work on nuclear reactors, every conceivable application of high pressure water jetting is in Jeff's wheelhouse, and he's been doing it for about 40 years. And almost 20 years ago, as he was operating in that field, some friends of his came to him, some hydrogeologists who knew about his work in the oil field, and asked him if there was a way to adapt this high pressure hydrojetting technology to water wells. And that was the beginning of the WellJet investigation and discovery and process. And so Jeff took that knowledge and applied it to the water well environment, finding the sweet spot in which high pressure water jetting would be effective in removing obstructions and incrustations from steel, but not be so powerful that it could damage the steel or PVC or any other kind of plastic well. Because in water wells, you have incrustations, you have buildup that develops on the inside of the well and in the perforated area and out in the wellbore formation. And those deposits adhere to steel, some more tenaciously than others. And what Jeff found in his research was that tenacious deposits would adhere to steel at up to about 14,500 PSI. So any kind of hydrojetting would have to obviously be capable of exceeding that amount of pressure in order to break the bond between the obstruction and the steel beneath. But on the other side of the equation, you have the yield strength of steel. And the yield strength of steel, depending on its composition, whether it's mild steel, stainless steel, high strength, low alloy, there's many different combinations, but the range of yield strength in steel is between 30,000 PSI and 50,000 PSI. So that sweet spot for using pressure technology to positively impact the removal of harmful deposits from inside water wells, but with minimal risk of damaging the intact steel, is between that 14 to 15,000 PSI and somewhere comfortably below 30,000 PSI. So that's where Jeff centered his focus and developed the WellJet technology to operate in that area. And that is what the system that he developed is based on. That's what the patent is based on. And over the last 10 years of applying the technology in the field, that's what our record of success has been based on. High pressure hydrojetting is a tool in well development and rehabilitation. So the big question always is for any well owner, whether it's a new well, an older well, municipal well, residential well, a well at a mine, a farm well, agricultural well. Why isn't my well working the way it is supposed to? Why is it not producing the amount of water that it's supposed to produce? Why is it costing so much money and consuming so much energy? And the answers are in the development process, could be inadequate for whatever reason, whether the conditions of the well made it difficult to employ normal development techniques, whether the well sat idly for a long period of time between drilling and completion, whatever elements have combined, whether there was some issue during the development of drilling fluid volume or containment, so that the well just didn't develop the way it was expected to. Another common problem, of course, is plug perforations. The perforations in the well that are designed to allow water to flow in so that it can be evacuated and pumped to the surface and do its job out in the world are plugged up with something. They are clogged in some fashion through incrustation, whether it's mineral or biological. The common ones, of course, are forms of iron bacteria, manganese, calcium carbonate, sometimes all three. Sometimes there is some sort of biofouling or slime that is encrusting the inside of the well casing and plugging the perforations. Then there can be blockages out in the filter pack itself beyond the well screen, between the well screen and the formation. There's usually some sort of filter pack or gravel pack that is designed to filter out fine sand or whatever is in the formation and allow the water to go through. Well, over time or even during the development process, that filter pack can become blocked or plugged with drilling fluid, with sand, with any kind of mineral incrustation that prevents the water from even getting to the well itself. Then there's also the possibility of residual drilling fluid in the near wellbore formation. As you know, and your audience knows quite well, during the drilling process, material is introduced into the hole that is being drilled that is designed to keep that hole open so that the well can be drilled and doesn't keep caving in. It's usually some form of mud, whether natural or synthetic, some sort of polymer, and that material is designed to keep the hole open, keep the water out, and keep the material of the foundation out of the hole, so that of the formation, to keep the material of the formation out of the hole so that the well can be drilled. Well, once that well is drilled and the casing is installed, a method must be pursued in order to remove that mud cake that was so helpful in drilling the well, but is not helpful in operating the well. And that's the development process. And often what happens during the development process is that, it has taken a long time to drill the well, and everyone is out of money, they're out of time, they're out of patience. And so when it comes time to develop the well, that development is curtailed or shortened or in some way. And what you want to be able to do is make sure that the well is as efficient and productive as possible. And sometimes that does not happen during normal development. You hit a particular target in terms of output or in terms of the amount of time allotted to the development process, and then you declare victory and walk away. So there can be residual drilling fluid and mud cake out there that has not been removed, and that can contribute to the well not working the way it is supposed to. So solutions to this problem, once you've evaluated it, you want to look at ways in which you can remove the incrustation, open the plug perforations, and somehow shake up and stimulate that gravel pack so that whatever blockages are out there are dissolved and the water can flow. So you want to be able to remove the incrustations, open those clogged perforations, break up obstructions in the filter pack, and restore the free flow of water. And there are many methods of doing this. Some of those methods have been around for a very, very long time. Putting a brush of some sort down the well, whether it is some kind of steel brush or nylon or fiber brush, and to brush off those deposits that have built up on the inside of the well. Another common and time-tested method is introducing chemicals, some kind of acid combination, which is designed to break down that mineral incrustation. And then there's some form of mechanical stimulation. This is designed to deliver energy out into the well and shake up the obstructions. You can use compressed gas. There's various methods of doing that, various forms of explosives from the old, farmer's method from the old days of dropping a piece of dynamite down the hole and seeing if you could shake it up, to various more sophisticated but explosive-based technologies, introducing some sort of pulse, sonic pulses, electronic pulses downhole, using some kind of a swab to flush water back and forth over the perforations and out into the gravel pack. And then there are different kinds of jetting, whether air jetting or hydrojetting. And the history of hydrojetting is that it began in the 1960s and with very, very low pressures, basically some form of garden hose kind of thing to put water downhole, a lot of volume, not much pressure, not much energy, and really not much in the way of successful results. And this method of jetting has been really discounted as an effective tool in water well development and rehabilitation for most of the 1960s through the 1990s. And basically because the pressures weren't enough to have an impact, and pressure was lost downhole over depth. As I mentioned in the earlier introduction, Jeffrey B. Glass, the president of Hydropressure Cleaning Incorporated, is the inventor of Well Jet. He began working on this process about 20 years ago. The field testing started in 2009. Commercial applications began in about 2010. The patent was awarded in 2012. And since that time, Well Jet has been operating successfully around the world in over 1,000 wells. The question about the effectiveness of hydrojetting is based largely on the lingering impact of the definitive study in the field by E. John List, the Analysis of Development Methods for Gravel Envelope Wells. which was written in 1990 and devoted its formulas and experiments to comparing swabbing versus jetting. And that analysis employs flow velocity field at the pack formation interface. Results of the study suggested that both swabbing and jetting can be effective development methods, but that swabbing appeared to be more effective because the efficiency of jetting was found to be conditional on the use of a filter pack size distribution that will enable filter particle circulation to develop. In the absence of this circulation, jetting is likely to be of limited use. Well, that was state-of-the-art analysis in 1990, but what has transpired in the interim is the development of more sophisticated and advanced methods, and that is why the profile of jetting has changed and the impact of jetting has changed, because the legacy analysis did not consider the increased energy delivery available using today's technology. And that is expressed by the equation E total energy, equaling E kinetic energy, plus E pressure energy. Due to the low pressure used in the analysis, 250 psi, only the kinetic energy was really accounted for in the analysis. The low pressure energy was really not an impact. Well, at today's jetting pressures of 15 to 20,000 psi, the E pressure value is 60 times greater than in that original analysis, and therefore is much more effective. Today's leading jetting systems are highly effective at delivering energy levels necessary to efficiently develop wells. And we see that the model that shows the typical trend over time of declining output and efficiency in a well, that can be disrupted by the well jet technology using that higher pressure and greater ability to deliver energy downhole and out into the filter zone and near well bore formation. And as we see from this picture on the right, the well jet process can remove those borehole interface materials that have reduced inflow. We see this large pile of formation sand and drill mud that was removed during a well development project that Well Jet was participating in. What is Well Jet? It's the sector-disruptive technology. It is revolutionary in the ability to utilize high enough pressure to overcome the strength of the deposits that are adhering to the steel and preventing water flow, or it also applies with plastic, but at different pressures and different tooling design. The patent is based on that high pressure water jetting, the ability to deliver a coherent jet that maintains laminar flow. That's in the nozzle design to deliver that jet out into the gravel pack. The self-rotating head that spins and is hydraulically removed from the well during jetting. So the incrustations are removed, the perforations are open, and energy is generated into the gravel pack and near well bore formation. All the elements of the process are adjustable to suit downhole conditions. And that's extremely important because every well and every circumstance has its own unique issues. And that information must be gathered and analyzed in order to successfully determine the protocols for rehabilitation. Typically, the range of pressure that Well Jet operates is 15 to 20,000 psi in steel, 4,000 to 6,000 psi for PVC and other forms of plastic well. Tool size is adjustable from anything from 2-inch monitoring wells up to pipelines, 6-foot diameter pipelines. The pressure obviously is adjustable, the rotational speed of the tool, the flow rate, and the retrieval rate. So everything is calibrated to suit the individual well conditions. As I mentioned earlier, tenacious deposits adhere to steel at up to 15,000 psi. A well jet operates in that sweet spot between 15 and 20,000 psi so that deposits can be removed, but intact steel is not negatively impacted. Have to deliver the energy downhole. It's one thing to develop energy at the surface. It's another thing to be able to deliver it 2,000 feet below the surface. And the well jet delivery mechanism is able to do that. Another factor is overcoming the environment. How can you penetrate? How can you deliver energy? And by using water, which is an incompressible material in water, the incompressible medium, you are able to overcome energy and inertia with energy and inertia. And that is one of the keys to the success of well jet over air-based or gas-based techniques. As I mentioned, the nozzle design provides that laminar flow, and you have to overcome the overburden pressure. And we do that with the exit velocity, which is between 1,700 and 2,000 feet per second. This is just a brief example for, there's various gas-based technologies. We did a comparison of one of those technologies called air shock. There's air burst, there's bore blast, there's sonar jet, there's a bunch of them. So the issues are that the fact that it's the pressures are lower, as we see from this 3,000 psi for the air shock. It's a compressible gas trying to transfer its energy in an incompressible environment, which is the water in the well. They use some kind of bursts to deliver their energy. And you see 260 cubic inches bursts of gas versus 7,400 cubic inches of water per foot. And then the way in which it operates using these pulses or blasts intermittently versus the continuous flow that happens with well jet. So you see that there's 5 to 7 times more energy, the fact that it's incompressible, greater energy delivered, and improvements in terms of the functioning of it. Let me go back, sorry. This is just a tool test in our yard, and you can see it operate. Typically, when we are testing it in the yard, we don't use the maximum pressure. We're just making sure everything is functioning. All the seals are tight, and all the nozzles and nipples and everything is operating correctly. I keep doing that. This is a field test when we're out on a job. Interestingly enough, that particular project was one in which this was a new well development in which a different sort of water jetting technology had been employed during the development process, but it was not effective or successful, and we were able to go in with well jet and be successful. The diagram on the left is the standard developed by the Water Replenishment District of Southern California that shows the basic decline in water well functionality over time. And the one on the right is a chart that illustrates the success that we had on a project in the Middle East, in Jordan, where it had been declining over time. They'd made attempts to rehabilitate it, but were unsuccessful. And when we applied our technology and process, we restored it to actually better than new functionality. And I'll get into that in a little more detail later. This is the Well Jet rig involving a 500 horsepower triplex diesel pump and the delivery mechanism. You see the hose set up there. This is one of our, these are different Well Jet rigs that are in operation around the world. We operate most significantly in California, also in Arizona, Nevada, Colorado. We've been to Texas. We've done a number of projects in Hawaii, and we're active in the Middle East. Right now, we are looking at some projects in Africa and Latin America and in Asia. This is us on a project in Hawaii. We've done a number of projects on the Big Island of Hawaii. Salinas, California, ag well. We do a lot of work, obviously, in the Central Valley of California. This is a project we were doing in Abu Dhabi in the United Arab Emirates for a hydroponic hydroponic agricultural facility. Quite interesting. You see, this is a tool test. You see the base plate there and the jets as the tool is being tested. There's always a lot of observers from the water agencies and consulting firms, etc. Tool test in Hawaii. This is another example of the tool being tested in the field. Yeah, and you can see the laminar flow, the coherence of the jet as it is emerging from the tip of the nozzle, and that's one of the keys to the penetration that we're able to achieve. And then we see various results. A vertical slot well on the left, before and after louvered casing, and this is an example of it. You see before and after results. Now, obviously, as we all know, what a well looks like is not automatically and conclusively indicative of how it will function, but it does provide a data point and a reference in terms of how it looked before, what was in the well, and how it looked afterward, what was in the well. So it is obvious, at least from the visual perspective in this particular case, you can see the improvement by the removal of deposits. This is a downhole side-by-side comparison of before and after the well jet rehabilitation process in a 30-year-old municipal stainless steel well. And we have another one. This is a vertical slot. Before and after, you can see before, obviously it's a cave, and afterwards you can see the gravel pack visible through the perforations, and that's one of the things obviously you're looking for is the removal of the obstructions, seeing the condition of the gravel pack so that it can allow the water to flow into the well. But of course, looks aren't everything. Performance counts. WellJet has a very, very long and distinguished record of successful output in terms of what the wells were doing before rehabilitation and after. But it isn't just gross output of water, but also efficiency. Is the well producing that water efficiently? Have you reduced the drawdown, the energy consumption, the cost of pumping the groundwater? And that is something that WellJet is very proud to be able to do, because that is the goal of any rehabilitation or development project, to increase the performance, the output and efficiency of the well, and to extend its working life. This is a case study, one of many. This particular well was a domestic water supply well. When it was drilled, it was producing 1,200 gallons per minute. It suffered problems over time. There were issues involving the quality of the water. So a filtration plant was constructed on the site. The well was shut down in order to build the filtration plant so that the water that the well produced could be distributed for human consumption. So once the treatment facility was completed, they went to, which took several years, and went to reactivate the well, and it was producing a little over just a few percent of what they needed. They needed 1,200 gallons per minute. It was producing 160 gallons per minute, and they had built this entire very expensive treatment plant to handle a flow rate of 1,200 gallons per minute. So we went in with the WellJet tool and we jetted the well, and it was test pumped after jetting. And I think on that project, we were working with a drilling company. We went in, we jetted it, then they did some swabbing and the removal of the fill after we jetted it, and test pumped it, and it was able to produce the required amount of water with lower drawdown even than when it was new. So when it was new, it was producing 1,200 gallons with 45 feet of drawdown. And then after we rehabilitated it, it was producing 1,200 gallons with less drawdown. So it was more efficient, more productive, and more efficient. And the well actually could have produced more water, but they stopped worrying about that because the filtration plant was calibrated for 1,200 GPM. This is a case study of an entire wellfield rehabilitation that we did for the Jordan Phosphate Mines Company in Eshadiya, Jordan. 21 wells rehabilitated. They were drilled in 1991, 14-inch diameters. Depths were between 750 and 950 feet. They averaged about 440 gallons per minute, but they've lost about half of that output, a little less than half of that output by the time they asked us to rehabilitate them. And they had tried some prior techniques and methods that had not been successful. So we went in with WellJet. We did the jetting with WellJet. We did dual swab surge blocking afterwards to remove the fill from the gravel pack. And then airlifted it out. So it was the jet to break up the deposits, the swab to pull those deposits out of the gravel pack and into the bottom of the well, and then an airlift to evacuate them. And we were successful in improving the flow rate about 122% over prior to rehabilitation, but interestingly enough, also improved almost 20% over what the performance was when they were new. So you see on the chart here on the right, the original flow rate of each well is the orange. The flow rate for each well prior to rehabilitation is the green. And the flow rate after the rehabilitation, which is the blue. In most cases, above the point of when the well was new. And speaking of new wells, WellJet is also useful in development for new wells, and we've been doing quite a bit of new well development recently. This is just one example from many, many examples and case studies. This was a well for a vineyard up in Santa Barbara County. The well had been drilled, it had been developed, it had been equipped, and it had failed. Okay. This is the profile of the well, 16-inch with wire wrap screen down to 1,180 feet. You can see the logs where the water-bearing zones are anticipated to be. The well was expected to produce 600 gallons per minute. It was unable to sustain even 250 gallons per minute, less than half of the desired output, without breaking suction. So the water was being pulled down to the pumps and burning them out. So we went in, we did the WellJet process, we followed that with the dual swab surge blocking and the evacuation of fill. We were able to solve the problems and get the well back online. It had been doing 275 gallons per minute and breaking suction. And then after the WellJet process produces 670 gallons per minute with 100 feet of drawdown, the specific capacity of 6.7, and significantly another 100 feet of submergence available for future needs. So the well is producing as expected and also has a cushion, and the decision was made to use a submersible pump rather than a vertical turbine pump to operate the well. So that is the overview and some specific details about WellJet. WellJet is an important tool in the process of well development and rehabilitation. It is not a magic bullet. It is not a standalone. You have to jet the well to break up the obstructions. You have to use some kind of surge block to pull that dislodged material into the bottom of the well, and then you have to evacuate it. So you have to break up the material, pull it into the bottom of the well, and evacuate it from the well to really get the complete benefit of the process of redevelopment or rehabilitation.
That was a great presentation. I picked up some stuff that I I didn't know about you guys. So, and just a couple quick questions because
Sure.
one of the things, and I'm really glad you brought up well development because it's really one of the areas we see that really gets underbid a lot, I guess you'd say, and there's never enough time devoted to well development. As a matter of fact, we usually tell our clients that if you're going to get hit with a change order, it's probably going to be for well development because
Right. Yep.
it's never it's never done adequately, and it really gets short shrift on most well jobs, and it's really a cause for lingering well underperformance. Is really the way I put it. So your techniques really, and we've actually gone to, at least on larger type well systems, we've actually gone towards bidding well development out separately, where we can do that because we want it done right. We want to start off with a good well, and it's something that's just a real problem that we keep seeing. So I appreciate you bringing that up. And any more thoughts on your your use of well jet technologies as a well development tool?
Yes, and I agree with you, and I've seen the exact same thing that you've seen. By the time it comes to develop the well, to finish it off, to punch the ball into the end zone, everyone's tired. They're frustrated. They've spent time and money, and so and often, as you know, often in the development process, it is handled either with a target in terms of output or a target in terms of number of hours of development. And it's something that's on the checklist to be checked off. Whereas in the actual development of a well, it is impacted by the process itself. If performance is continuing to improve, development should continue to improve if what you're after is the most productive and efficient well. So it's a challenge from the well owner side because of the cost and the time. It's a challenge from the drilling side because the bulk of the value for the driller is in the drilling and getting it and then moving on to their next project. And so you have to try to find a way to balance those two priorities. And also for us with WellJet as a development tool, we say to everyone who will listen, WellJet can shorten the development time because of the energy that we can deliver down there, so that if it were to be included as a regular part of your development rather than an emergency or add-on or redevelopment request when the original process wasn't successful. And sometimes we're successful in doing that, but typically most drillers are protective of their own process that they use, and they don't want anyone else getting involved in that. And that's completely understandable in the abstract. But in practicality, there is a benefit to it. We did the first project we did in the Middle East. They only turned to us because they had completely exhausted everything that they had in their own toolbox. And that's understandable because you don't want to bring people in from halfway around the world if you don't have to. But in that particular case, it was necessary, and we were successful in improving the efficiency of the wells. So our perspective is we can always help. We would love to come in as a regular part of the development rather than later as redevelopment. But whenever we have the opportunity, we try to do the best that we can. And your idea of having the well development be a separate piece entirely is quite interesting, and I've heard it from some other consultants as well, for exactly that same reason. They want the well to produce at its best, and they want to use a method, whatever that method is, that will give them the best chance of getting that result.
Okay, thank you. And here's something I tend to deal a lot with wells that have problem issues. I mean, my my main focus is really on, diagnosing and solving well problems, which means that wells have been around for a while. And
Right?
I was just recently looking at one. We did a video on it. It was originally built in 1947 in Southern California,
Okay.
and remarkably, I mean, it looked pretty bad when we did the video, but not as bad as you might expect for a
Mhm.
1947 well. However, it's really probably time for them to get a new well, but that's kind of an extreme example. But really getting into wells, and you're dealing with some high pressure techniques, and I know you talked about it or touched on it a little bit earlier, but how do you really evaluate whether a well is appropriate for your methodologies, and we're not going to do any damage? Because I look at some and I just say, I'd go in there with a light brush, and that's probably about as good as probably about as much as you want to do, because it's probably not going to hold up to any more aggressive techniques. And so we tend to run a video usually before we do well rehab and some other techniques to really kind of evaluate the well. But what's your methodology that you really look at to determine whether your technique is going to be a little too aggressive?
Well,
And I know it's kind of a dicey thing, sometimes it's a tough call, but
well, as you know, there's no way to be certain that doing anything in a well will either be effective or be 100% risk-free. Sometimes you can even put a little light brush down there and the thing can cave in. So you do want to try to understand to the best of your ability the actual condition of the well. The video is helpful because it provides visual evidence. You look at the column pipe and the pump and the bowls and see what their condition is. Have they, really badly deteriorated? Does that indicate that the well may be having some issues of integrity? And speaking of integrity, there's also the CITM tool, the casing integrity and thickness measurement, which is not foolproof, but is a great piece of data. And we've used that on a number of occasions where we've seen the CITM. It has identified questionable areas in which the wall thickness may be have corroded and have been reduced. And so what we do under those circumstances is be aware and adjust the process to take that into account. With older wells, particularly really old ones like you're talking about, more than half a century, you have to look at the big picture and think about what is the goal of the well owner. Has this owner basically given up on this well and is planning to drill a new well and just wants to take a shot to see if he can get another couple of seasons out of it? Or is this his lifeline? And if it makes 10 gallons or 1,000 gallons, he needs it working. So you have to take that into account. We've gone in on wells that were considered dead, that were about to be formally abandoned. And we've been successful in bringing them back, even old ones from the 1950s. But you have to be aware of everything. We jetted a well. This was for a water district. And it was drilled in the 1950s. And when we finished jetting and did a video, I mean, there were many holes. There was much deterioration. You could see the corrosion. The well still held together and it still had its gravel pack, but it required a bunch patches to continue because we had exposed the difficulties in the well. Now, that was a case in which it all worked out, but you have to consider every factor. It's not foolproof. It is not 100% guaranteed. Sometimes wells are so, as you mentioned, they are so corroded that the only thing that's holding them together is the incrustation. And if you remove that incrustation, what you're left with is, steel there's very little left of the intact steel. So you have to take it into consideration. I'm trying to think of off the top of my head a well which we simply said we can't do anything. We're not doing it. What we usually do is the more questions we have or the more concerns there are, the more conservative we become. So we will use a smaller tool. We will use lower pressure. Whatever it is, we will adjust it. We might retrieve it more rapidly. Whatever it is, our goal in the design of the use of the tool is to positively impact the well and not exacerbate any existing problems that are there.
Great. Thanks for mentioning the CITM tool too. I'd forgotten to mention that, but that is a great tool for measuring the integrity of the casing. Like you say, it's not foolproof, but
it's,
it really
it's
gives
very
you,
helpful.
yeah, it really gives you an indication of how much corrosion you've had, and the especially if you know what the original thickness of the well wall is, then you can compare it to what the CITM is telling you, and really see how much corrosion, how much you've lost to corrosion. So great
Sure.
tool. Just last question here is, and you touched on it a little bit in your presentation also, is combining WellJet with other techniques.
Yes.
Maybe you can speak on that a little bit, how you do that, because usually it's not. I tell people with well rehabilitation, there's probably not just going to be one tool. It's probably going to be a combination of things, especially if it's never had a rehab or it's been a long time. You're probably going to look at a sequence of tools in there. So maybe you can talk on that a little bit.
Yes, that's a very good point. The sequence of tools and the elements involved in development and rehabilitation. WellJet is an extremely powerful tool. There is nothing like it anywhere else on the market. It's unique. It can deliver more energy downhole than anything else. So what we can do, no one else can do. That's wonderful, but it is not a magic bullet. It is not the be-all and end-all. When you are rehabilitating a well or redeveloping or developing a well, you have to consider all of the elements. What the jet does is it removes incrustation, it opens plug perfs, and it breaks down whatever blockages are out there in the gravel pack. That's it. Those broken down deposits are still out there, unless the aquifer itself is so incredibly active that the mere inflow of water is going to pull all that debris out of the gravel pack and into the bottom of the well. So there has to be some kind of tool to pull that stuff in. And we usually use a dual swab surge block that can operate with an upstroke that has enough velocity to make sure you're getting good suction to pull that stuff in. And then you remove the fill from the bottom of the well, airlift, bale, whatever is appropriate for pump, whatever is appropriate for the individual circumstances of the well. So we always have partners that we work with. We work with different contractors, different drillers, pump companies, consultants. WellJet is not the Lone Ranger. It's just a very, very powerful and effective tool that can accomplish things that others can't. But it is only as good as every other element in the process. Now, we have done wells where, for whatever reason, time or budget or inclination, the well owner has said, this is all I'm doing. I'm just going to use the WellJet, and then I'm putting my pump back in the hole. And It can be done. It has been done successfully. The risk of it is if there's a tremendous amount of material that's out there, and now you put your production pump and bowls in the well, and you start pumping and you pull all that crud in, it could very well clog up your pump, chew up your bowls. So you have to balance that. You want to get that stuff has to be evacuated. You got to get it out. But if you are doing it with your own production equipment, it could end up being quite risky. So it's not something that we recommend. We've done it on projects where, for need and exigent circumstances, it was done, but it's not what we recommend.
Great. I think that's all the questions I have. Any final words? I will put your contact information back up here at the end too, so people can get a hold of you. But any final words?
Just wanted to thank you again for the opportunity to talk with you and your audience. I really appreciate it. I love to talk about WellJet. I love to talk to well owners, to drillers, to pump companies, to consultants, to talk about the challenges that we all face and the solutions we try to come up with. And what we do is unique. It's very powerful. It's very effective, and it forms an excellent link in the chain of well development and rehabilitation.
Charlie, thank you so very much, and this has been very informative, and we really appreciate your time. Thank you.
Thank you so much, Tom. You have a great day, and I'll talk to you soon.